All right, today we're going to tackle this problem from the 2020 CCC, that's the Canadian Computing Competition. This is the junior problem number 5 and senior problem number 2. So let's kind of walk through the question here. So the goal is we need to determine if it's possible to escape from a room. And this room is an m by n grid with each position, the cells, containing a positive integer. So the grid is m by n, and the rows are 1 through m, and the columns are 1 through n. So I've drawn it out over here for us to kind of visualize. We have m rows starting at 1, going all the way down to m, and we start at 1 for the columns and end at n. So m by n. And we can use the notation RC to refer to the cell, and there's going to be a number in the cell. So for example, here, X, in row R and column C. That's kind of our notation that we're working with. Now we start at the top left corner, which is row 1, column 1, up here. And we exit at the bottom right-hand corner. So somewhere down here, column N, row M. So now if you're in a cell that contains a value X, then you can jump to any cell, any other cell, AB. So this AB refers to the row in the column. As long as it satisfies this equation, A times B is equal to X. So what that really means is that if you're in a cell, say X, then we need to look for the different factors, two numbers that are going to multiply to X, and we can jump to those different cells. So they give an example over here. For example, if a cell contains a 6, and there are 4 different cells that we can jump to: 2, 3, 3, 2, 1, 6, and 6, 1. If you multiply any of these two numbers together, you will get the 6. And we have to keep in mind that if you have a 5 by 6 grid, there actually isn't a row number 6. So there are fewer possible jumps. We actually can't make it to this one. So now we kind of understand the problem here. We're starting in the top left corner. We're going to have some numbers here, and we're able to jump to different cells. And we want to figure out if we can make it to the end of the room, which is on the bottom right-hand side. So let's take a look at what the input looks like. The first line is M. So remember, M is the number of rows, and the second line is N, number of columns. This is going to be both numbers between 1 and 1,000. And then the remaining input actually gives us the cell, or it gives us the grid. M lines, because there are M rows, and then each one is going to have N positive integers, each less than or equal to 100, and separated by a single space. There's some information here regarding the marks, but I'll skip that for now. And let's take a look at the sample input down here. So we can see that the first number is a 3, and the second number is a 4. So that is our M and N. Number of rows is 3, and number of columns is 4. So that's why there are 1, 2, 3 rows over here, and then 4 columns of numbers. And this really makes up our grid. And the grid is filled with positive numbers. We got 3, 10, 8, 14, so on and so forth. And the output for the sample input is yes. So what that means is you can start from the top left corner and jumping throughout the grid. You're in the room here. You somehow end up at the bottom right-hand corner, following the rules that you can only jump to grids that satisfy this equation. So you can only jump to cells that have the factors of the number that you're in. So let's walk through this in a bit more detail down here. So starting from 1, 1. So in cell 1, 1, we have a 3. If we have a 3, then that means the different factors are 1, 3, and 3, 1. There's 2. So there's 2 different paths that we can jump to. We can jump to row 1, column 3, which is the 8 over here, or we can jump to 3, 1, row 3, column 1, which is the 6. Now, we might want to just start with one of these paths. Maybe we'll go the root of the 8 and see where that takes us and see if that leads us to the 9. If not, we have this other opportunity to go to the 6 and see where that will take us. For example, if we go to the 8, so that's over here, row 1, column 3 gives us an 8. We can list out all the different factors. But notice that most of these are sort of outside of our grid. For example, 1, 8 is a row of 1 and a column of 8, but we don't have 8 columns here, we only have 4. So most of these are invalid, essentially. We don't really need to worry about them. We can only land at 2, 4. Row 2, column 4 leads us to the 12. And now we want to repeat this process. We're in the 12, or we're in a cell that has a number 12, and we consider all the different factors. Again, most of them are not valid outside of our grid. We don't need to worry about them. But we do have this one over here, which is 3, 4. Row 3, column 4, and that is actually the end of the room. So this path over here, starting at the 3, jumping to the 8, because it's in position 1, 3, which was a factor of 3, and repeating that process over and over again leads us down here to the 9. So we have one path that allows us to escape the room, and therefore the output was yes. Now, we could have also tried some different pathways. So we could have went to the 6 and then looked at different numbers that would, the different factors of 6, and then we could have bounced around, and actually we do end up finding a success path. So we can kind of explore that in a bit more detail. You can kind of see here that we kind of create like a tree, like you start in the column 1, row 1, which was the 3, you start up here, and you potentially have different cells that you can jump to. And from those cells, you have other ones that you can jump to. Maybe this one only has 1, and this one has 2. You can keep going and you can keep going. And the question is do any of these lead us out of the room? So can we find a success path jumping around and bringing us to the end of this room? You can imagine that a lot of these paths might be dead ends, and a lot of these paths might actually just be kind of jumping back and forth. We can almost get stuck. You can imagine that we're on the grid and it kind of brings us around in a circle over and over again and doesn't really bring us anywhere. So we'll have to watch out for that. So now that we fully understand the extent of the problem, we can start to come up with a solution. You might be thinking loops might help us here because we basically want to jump for all the different options on a cell, and then we want to repeat that for the next cell and the next cell and the next cell. When we have this sort of format, one of the structures that we can use is recursion. So what we can do is our sort of simple function that we want to do is jump from a starting cell, jump to all the different possibilities. And from those possibilities, we also want to jump, and we kind of want to repeat that over and over again. So it's the different layers here of this tree. So I also want to bring up that there's potentially another alternative to solving this problem rather than starting from the beginning. When we start from the beginning, we end up going down all these different paths, and it's not really clear whether or not that path is going to lead us to the end over here until the very end. An alternative is we can actually work backwards. If we start at the 9, we know that we are in column 4 and row 3, which is equal to 12, which means in order for us to jump to the 9, we had to be at a 12 beforehand. So we can go and find all the positions of the 12s, and there's 2 of them here. Row 2, column 3 is this one, and row 2, column 4 is right beside it. We can start just at this one over here. So we'll start at 9 and then end up going to this 12. And in order to get to this 12, we would need a 6 because this is in position column 3 and row 2. So we can go and find a 6. So we're kind of working backwards here to see if it's possible to get to the 12 and then possible to get to the 6 now. The 6 is in position row 3, column 1. 3 times 1 is 3, which means we would have to get to a 3. And that 3 is actually the starting point. So by working backwards, we sort of found this path going forward from 3 to 6 to 12 to 9. So the reason why I like this solution better is because we potentially avoid a lot of dead ends, where if we start at the 3, we don't really know if we're going to end up down here at the 9 until we actually explore all the different options. So let's take a look at putting this together. So let's just jot down sort of the high level game plan to solve something like this. So first, we'll probably want to read the data. So I'm going to have the data in a text file. And we understand the format as basically, we have our MN and then we have all our data. So we understand the format. And then so remember we're starting backwards. So we're going to start in position MN. So M is the row and N is the column. We're going to start at cell MN. And what we want to do is we want to find all cells that equal M times N. Remember, the reason we're doing that is because in order to jump to this position, the end state 9, we needed a 12 because 4 times 3 is 12. So the general case is that this is going to be M and this is going to be N. So if this was a different size grid, you have something like this. M is going to equal to 2 and N could equal 3. So we're going to find all the cells that equal M times N. We're going to check if any are the top right starting position, which is 1, 1. And if not, jump to those valid cells and start over. So really, we're going to start steps 2 through 5. So these are the steps that we want to repeat. We want to start at a new cell, find all the cells that equal M times N, and then see if we can jump to any of those cells. And if it's the top right position, then we're done because that's the start. So if there was a 12 up here, then we would have been done just in one step. Because 3 times 4 is 12, so we could have potentially started at 12 and jumped all the way to 9. But if not, like in this scenario where the 12 was over here, we have to repeat this process. The new number is 3 times 2, because that's the position that we're in. So we need to find a 6. And that's not the starting point, so we have to repeat it again and again. All right, so let's start coding this up. First thing we want to do is read the data. So we can say with open data.txt, and we're going to specify that we are just in read only as file. So this opens this file and we can access it with this variable over here, file. The first variable M is going to be file.open read line. And is going to be the next one. And we're going to have to convert these into integers. When we read something from a file, it's going to be in a string format. Now we want to read all the data. So read grid data. We know that there are going to be m rows, so we can iterate m times. And we can do, we can say the row is equal to file.read line. And I want to save this information in sort of like a list of lists. So the first thing I'm going to do is split it. The split function takes the string and we'll split it up based off of the spaces in it. So for example, if we have a line of text like this, when we read the data, it's going to be one row or one line, a whole string. And after we split it, we'll have a list 1, 2, and 3. Now, again, we also want this to be in a int format. So for that, we can use the map function. This will take everything that has come out of this and apply the int function to each one of these. Now we've kind of moved on from here to having integers. And we need to wrap this in a list. So let's check if that worked. And we're going to want to store this in another list. We can call it data. We'll add that row to data, so it'll keep track of everything. Print data. So you can see when we run it down here, we get the output. And you can see all of the information. So let me pull up the text file. So we have 3 and 4, which are m and n respectively. And then we have all the data here. And we have it in a list format. Perfect. Okay. So the next thing we want to do is we want to start at, get rid of this. We'll call it the endpoint, which is m times n. So this is the 12. Pull it up again. Or actually, I'll pull it up here. So 4 times 3 is the 12 that we're searching for. Now we want to find all the positions in the data variable where the cell value is actually equal to this m times n, which is 12. And there's actually a pretty easy way to do this. We could do like a double for loop. We could say, you know, for each row and each column in our list and check if it equals this. But there's an easier way if we use NumPy, which is a package in Python to do some numerical calculations. And we'll say array is equal to NumPy array data. So now we'll convert it into a NumPy array. And the locations, we can use arg where array is equal to n. So what this does is it checks each cell in array, checks if it's equal to n, and it tells us the position. So let's print this out. Locations, do a line break, and we'll use this format. We need an F over here. So this will tell us this will tell us all the locations where the data is actually equal to that 12. When we run this, we get 1, 2, and 1, 3. Let's relate that back over here. 1, 2, and 1, 3 seems a little different than what we had over here. Specifically, it's off, each one is off by 1. So instead of 1, 2, we wanted 2, 3. The reason for this is that the NumPy array starts indexing at 0. So an index of 1 is actually the second row. This is perfect. This tells us the row and column, the locations of the 12s. So the next thing we want to do is we want to loop through for mn in loops. So let's loop through all the row, the combinations. And if m is equal to 0, which means we're in the first row, also n is equal to 0, we can print yes. Basically means that we've found a location that's in the upper left-hand corner, and we're done. We can print out, yes, there is an escape. But otherwise, we want to continue. We want to repeat this process for the new. So this is where recursion can kind of come in handy here, because we basically want to repeat this process. We want to assign a new n value. We want to find new locations, and we want to check if any of those locations are in the top right corner. So to implement recursion, we're going to call this we're going to give this a function name. We'll call it jump. We're kind of jumping around the grid here. And we want to check the locations where it's equal to a value. So the value, the parameter that we're going to pass on to the function here. So now if we want to repeat this process, we can also check, and instead of printing yes, we'll return true. There's an end state. Otherwise, we want to check if we jump to another cell, and the new cell value is going to be m plus 1, and n plus 1. Why are we adding 1? Because remember, these index values start at 0. So when we got a value of 1, 2 down here, what that really meant was 2, 3. It meant that there was a 12 in position 2, 3, row 2, column 3. And when we multiply that together, that's how we know we need to get to a 6. So if this also works, we can return true. You can imagine that we have two different options for 12. So we can kind of move this down here. So if jump end, we'll print yes, and else no, and n is still this value over here. So we're going to check if we can jump from m times n, which is the endpoint, goes through here, finds all the different values, and then we need to loop through and check all those different locations. If it's equal to 0, 0, then we're done. But otherwise, we want to keep digging deeper and deeper. So if we look back to this sort of tree here. We start here, and then we change the color. We go down here, and we try the first cell. And if that doesn't work, we check the next one. And if there's more, we keep checking. And if that's no good, then we can come back up and check the next one and the next one. And if that was no good, we'll come over here and try the next one. So this allows us to go through all the different combinations. Now, if there are none, if there's no way to jump to 0, 0, then we want to return false. We need to make sure that that's outside the for loop. So if we go through this whole for loop and we don't return a true, then we can return false. So let's see what sort of output we have here. We are printing the locations. That's probably okay. We can print value as well. Use squiggly brackets with an F. Print the variables. All right, so let's run this and see what happens. All right, so the first time around, we get a value of 12 because that's the number that we're trying to jump to. We started at the end here, and 4 times 3 is 12, so we're trying to find a 12. And it found 2 different scenarios. The first one, it goes to the first one, and that was a 6. It was happy, it found a 6 in location 2, 0. So we can pull this up. Remember, 2, 0 is actually 3, 1, and we add 1 to each of the index. And then it's looking for a value of 3, and it actually found one. There's a 0, 0 here. So it had to go through all these different combinations before it could find a yes. For fun, let's see what happens if we change this 6 to a 0. Basically a dead end. We can't find a 6. Let's save that, rerun it. So you can see here, it's looking for the 12s. It's looking for a 6, and it doesn't find one. And now it's looking for an 8. And that's because this cell over here, 1 plus 1 is 2, and 3 plus 1 is 4. 2 times 4 is 8. So it's trying to find an 8 to get to this 12. So you can see it found a dead end, and it kept going to the 8. For the 8, it needed to find a value of 3, and it basically led us right back to where we started. So you can see how we're kind of working in this kind of tree structure, looking at all the different combinations. Now, there's also scenarios. For example, let's look at this one over here. This is a 2x2 grid. We've got 6, 4, 4, and 4. We're going to start here, and it's going to search, because this is position 2, 2 is going to search for 4s. And it's going to find all these 4s. And it's going to go over here, and it's going to be a 2 and a 1, and it's not going to find a 2. But because we're going to find all the locations of the 4, it's actually going to get trapped, and it's going to just keep trying to get to this 4. You can imagine it's just jumping to this 4 over and over again. So let's change this to data 2, try out a different file. You can see we end up in an infinite kind of recursion here because it just keeps jumping over and over and over again. So to try to solve this problem, I'm going to propose that we keep track of what we've searched. Let's have a list of search, and basically keep track of which cells we've gone to. We can append MN because we're going to start by going to the cell MN. And down here, we only want to repeat this process if MN, so if that pair is not in search. So if we haven't already searched it before, then we can search it. And here we want to add MN so that we know that we've now gone through it. So now when we run this, well, if MN is not in, I get rid of is, so if MN not in search, so you can see here it finds 3 locations of 4s. Let me pull it up again. We're in position 2, 2, so it's looking for all the 4s. And now it's trying to find values of 2, doesn't find any, tries to find another value of 2, so that's these 2 up here in position 1, 2. And then it finds the 4 again, which is this guy right here. But it knows that it's already searched for it. So it does not continue to search because then it would just repeat over and over again. So that's how we end up with a solution of no here. Awesome. So to recap, we are trying to solve a problem here where we have to figure out if there is a clear path from the start to the finish. We decided to start backwards, look at finish, look at this finish number, and see if we could get back to the starting point. We do so by trying to find numbers that equal the product of the column and the row. As we know that if we're at a 12 here, we will be able to jump to this column because 3 times 4 is 12. We repeat this process recursively to see if we can end up in this top right position. Awesome. So I hope this video was helpful. If you have any comments or feedback, feel free to share it in the comments below. Thank you very much.